Good morning, everybody. Hope you're all healthy and safe. We are going to move on to the last section of our first module, that is section 2.6, numerical methods. So, in this section, what we are going to discuss is there might be many differential equations which will be practically not possible to solve by the methods that we have learned so far. So that is when the picture of this numerical method comes out. So that is they have many differential, if you consider the practical case, many differential equations possess solutions, okay, but these solutions cannot be found out analytically. So like by analyzing the differential equation, like we cannot check whether it is separable and so on. So far the methods that we have learned so far may not be applicable to find the solution. So in that case we use the numerical method, okay. That is, the differential equation is used as the cornerstone of an algorithm for approximating the unknown solution. So when we use this numerical method, we won't get the correct solution, we will get an approximate value to that solution, okay. So we are going to discuss about the numerical methods which will help us to solve a differential equation. So in this we won't be detailedly studying all. There are many methods, numerical methods to solve the differential equation but we shall be discussing only on Euler methods. We'll be just discussing the method and we'll just do a problem related to that. So before that we have to understand how to apply this Euler method, or how is it used. So for that we have to know a term called as linearization. Now, so in your textbook you can see as an example, this linearization is a method in which we use the concept of tangent line. So you can see that an example is given. We are given an initial value problem, okay, that is, it's given by y dash is equal to 0.1 root y plus 0.4 x square, comma the initial value is y of 2 is equal to 4, okay. So what we are going to do is we are going to this differential equation will have a solution. So let us suppose that the differential equation solution is y of x, okay. So we are in this example we are going to calculate the value of y of 2.5, okay. So for that, first of all we will draw the direction field of this differential equation, and if you see we are considering the direction field only in integer values because we have the initial value y of 2 is equal to 4. So what we do is we determine these are the linear elements, the arrows are the linear elements. So you can see this is a solution curve. So all these are determined with the help of softwares. So this is a solution curve, the blue line. So you can see that the linear element actually they come closer to the solution curve and form a tangent to the solution curve. So what we do is we determine the slope, okay, that is given by f of 2 comma 4. Now here f of xy is clearly 0.1 into root y plus 0.4 into x square. So we'll determine what is f of 2 comma 4 and we will get it to be f of 2 comma 4 is nothing but 1.8, okay. Now using the point 2 comma 4 and the slope 1.8 we can find the equation of the line, okay. That is what will be the equation of this particular line, that is the solution y of x. This is a solution curve. So if you are able to find the equation of this line to which the tangent line has a slope m is equal to 1.8, then that will give us the value of that line. I mean, it will give us the equation for that line segment. So here that particular equation, so what is the point slope form? It is y minus y dot is equal to m into x minus x dot, okay. So here m is known, m is 1.8, y dot is 4 and x dot is 2. So with the help of that we will get y is equal to 1.8x plus 0.4, and y is denoted as L of x. So this is called as the linearization of y of x, which was assumed to be the solution at the point x is equal to 2. Okay. Now similarly, this can be used to approximate values. If we consider the smaller neighborhood of the point 2, then we can find what is the value of L of 2.1. okay, approximation will be as such. So like this we can find the value of L of 2.5, which is the required value if you have to determine it. Okay, so I hope you have got a small picture of the linearization concept. That is, we'll be using the tangent lines, that is the linear elements will form the tangent line, and with the help of the point slope form, which is an initial value problem, so we know a point, with the help of the point slope form we'll be able to find the linearization. So the same method is just used for, or we use the linearization concept for solving Euler's for the Euler's method also. So in Euler's method also, what we do is we use a linearization of the unknown solution y of x at the point x equal to x dot. Okay, so that will be instead of y, we are writing it by L of x. F of, this is the same as a point slope point form, right, where f of x dot y dot is the slope at the point x dot y dot. So f of x dot y dot into x minus x dot plus y dot, this will be the linearization of y at x equal to x dot, the same thing that we have seen in the previous example. So now what we do is we are as we mentioned, this is actually the approximate value, right, approximation. So if you want to find a particular value, we have to bring it to that value from the initial point that is given to us. So we were given the point 2 in the example. From 2 we have to reach, or we have to find the value of y of 2.5. so you have to find step by step, you have to increase the value and determine the value. That is the numerical method. So here what we do, first of all, instead of x we will replace x by a small change, that is x is moving a little bit, x dot to x1, where x1 is x dot plus h. Okay, so instead of x in this equation, we will replace it by x1, where x1 is x dot plus h. Okay, so what will be the value? L of x1 will be f of x dot y dot. All other values remain same except x. X will become x1 minus x dot plus y dot. Now x1 is nothing but x dot plus h. So x dot and x dot gets cancelled, so it will become h. So L of x1 will be equal to y dot plus h into f of x dot y dot, and we call L of x1 by y1. So we get y1 is equal to y dot plus h into f of x dot y dot. Then next what we do, we replace x1 by x1 plus h. X1 will be changed to x1 plus h, so that will be x2. Okay, so here you can see x2 will be x1 plus h. Now we will get x2 is x1 plus h, so L of x2 will be correspondingly f of x dot y dot into x1 x2 plus h minus x1, and in this case when we move to the next step, our initial point will be x1 y1. Okay, so in the first step initial value was x dot y dot, and we've brought a change, we replaced x by x1 plus h, x1 which is x dot plus h, sorry. And in the next step x1 y1 will be our initial value, and we'll bring about the change. X1 will be replaced by x2, and x2 will be nothing but x1 plus h. Okay, and so on. So proceeding like this, in the end the general formula will be y of n plus 1 is equal to yn plus h into f of x n yn. So the procedure, this process of using tangent lines successively is called as the Euler's method. Okay, so just you have to keep in mind the corresponding formula, that is a general formula that we have seen, that is yn plus 1 is equal to yn plus h into f of x n yn, So this is the Euler's method. In this method we usually use the linearization concept, okay, linearization of the unknown solution, and proceeding just now that I have mentioned, proceeding successively or recursively, we will get the general formula, that is yn plus 1 is equal to yn plus h into f of x and yn. Okay, so this is the Euler's method. So now let's just see a particular example which is given in your textbook. So we'll move on to the example, that is example 1. We are given the initial value, that is the initial value problem is y dash is equal to the same thing that we have seen in the example, and we are asked to find the approximation to y of 2.5, and there are two values of h. One is h is equal to 0.1 and the other is h is equal to 0.05. Okay, so here f of x y is 0.1 into root y plus 0.4 x square. Then what will be yn plus 1? So first of all, when n is 0, we'll have h is 0.1, x dot is 2, y dot is 4 and n is 0, so we'll get y1. y1 will be y dot plus h into f of x dot y dot, so the value is coming out to be 4.18. Then we'll find what is we have to replace, or if it is 0.05, if we use h is equal to 0.05, we can find y1 is nothing but 4.09. Now once we know y1, we'll determine y2, and for that y2 will be equal to y1 plus h into f of x1 y1. So here x1 will be the value that we have obtained, that is x dot plus h2 plus 0.05. Okay, so I hope the method is simple. You just have to replace the values, just remember the formula and successively repeat the procedure. So the question arises, when should we stop, right? So that is, first case is h is 0.1, so our initial value was 2, so first x is replaced by x dot, that is 2 plus h, that is 2.1. okay, so this is 2.1, so the next value would be 2.1 plus h, that is 2.2. so when we use h is equal to 0.1, we'll have to repeat the process 5 times. okay, and when it comes to 0.05, when h is 0.05, we'll have to repeat it 10 times, then only we'll get the value y of 2.5. So proceeding like this, here they have used the calculator, so or they have used a particular software, so you'll have to do it by calculator. You can see that proceeding like this, you'll get first case 2, 2.1, 2.2, 2.3, 2.4, 2.5, and approximate value will be 5.0768. And in the case of h is equal to 0.05 is also given, we'll have to use 10 steps to obtain 2.5. So that is just calculation by hand, which we can find the approximate value. So the problem is simple. Will be given the initial value problem, so you'll have to determine what is f of xy, and then we'll be able to determine what is x dot and y dot, and then just use the h value given in the question to make the increment, and just stop when we reach the point that we are asked to find the solution. So just remember the general formula, yn plus 1 is equal to yn plus h into f of x and yn. So that is our Euler's method. So don't forget the formula that we have seen, and we shall be doing some problem to just get into the picture of it, or how we can solve the differential equation numerically. So that's it for today's session. Thank you. Stay safe, stay healthy.